there, press that, yeah. And then share your screen again. So, we're just gonna, for everybody who's online, we're just gonna record Yisa's presentation part of the defense, and then we will turn the recording off at that point.
So this is the right one.
There's a slideshow. You want to put the slideshow?
Yeah, there, yeah, perfect.
All right. Ready, Yisa?
Yes.
Okay. So welcome everyone to the PH defense of Yisa Gineth U. I am the chair, Dr. Eric Peterson. I'll be administering these the proceedings. Just to a bit of a background, Yisa will have 40 minutes to give a short presentation on his work, summarizing the main points and main concepts, then followed by rounds of questions from the examining committee. Each committee member will have 10 minutes per question. The thesis advisors, because they're co-supervised, have agreed to share their time, so they have 5 minutes. And the questions can be anything pertaining to your work. I'll be monitoring the time to make sure that everyone's on track. People on Zoom, hopefully you can hear us all right. Please make sure your mics are muted, just so we don't have any background interruptions. Otherwise, Yisa, do you have any questions before we proceed?
Well, no.
Okay, well, you're welcome to take it from here.
Okay. So thank you, Dr. Peterson, for giving me the floor. Good morning, ladies and gentlemen, and welcome to my PhD defense. So the title of my dissertation is on mapping land use change in the Congo Basin, machine learning approaches to land cover monitoring, projecting forest cover change under IPCC climate change scenarios, and modeling large mammal habitat suitability. Deforestation and land degradation is accelerating worldwide, and according to United Nations Food and Agricultural Organization Forest Assessment Report in the year 2020, as well as other reports generated by the World Resource Institute, over 420 million hectares of forest have been lost worldwide over the last 30 years. In a study by Curtis et al. In 2018, they showed that these forest loss are as a result of increased socioeconomic and changing disturbance regimes resulting from human-driven climate change, as well as human population growth or density, for which, according to a study by Curtis et al. In 2023, as well as Stephen et al. In 2015, represent a partial indicator for a combination of anthropogenic drivers, impacts, and pressures arising from economic neocolonialism. So these problems are generally acute in the African tropics, especially in the Congo Basin, where the intensity of human activities is increasing and the effects of global warming expected to increase in severity. That is, mean annual temperatures are expected to rise by over 2 to 4 degrees centigrade by the end of the 21st century. The Congo Basin is actually situated within 6 Central African countries, including Cameroon, the Central African Republic, the Democratic Republic of Congo, the Republic of Congo, Gabon, and Equatorial Guinea. The region covers a total surface area of approximately 4.2 million kilometers squared, constituting the second largest tropical forest in the world after the Amazon Basin. Now, because of its rich diversity, as well as a continued loss in biodiversity, the 6 countries surrounding this region established a number of transboundary landscapes, as well as protected areas in the year 2000 under the Commission of Central African Forest Agreement. In the year 2013, a study by Mayo et al. Showed that the Congo Basin is covered with a dense forest cover of over 178 million hectares. But in another study by Tiokabina et al. In 2018, they showed that these forests have been lost at rates of over 1 million hectares per year as a result of socioeconomic and climate-driven disturbances such as anthropogenic fires, industrial selective logging, small and large-scale clearing for agriculture, mining, and road construction. And according to this study, there is an anticipated 5-fold loss in forest cover expected by the end of the 21st century. So this together shows that forest loss is contributing to large-scale changes in forest cover and land use patterns in this region. But despite this evidence, limited information is available in the scientific literature on the trends in land cover change for the entire Congo Basin and on how this will look like in the future. Limited information is also available on the contributions of these human disturbance factors to land cover change in this region. Several studies have attempted to map land cover change in this region, but the problem with these studies are that they are either limited to a very smaller geographical scale or to a very short time period. There are other several land cover products that are freely available for this region within the Copernicus Global Land Cover Project of the European Land Monitoring Service. But the problem with these data sets are that they are limited to the year 2015 to 2019. There are other several land cover data sets contributed by various nations within the United Nations Food and Agricultural Organization database. But the problem with these data sets are that they are either incomplete or lack consistency in geographic coverage and data collection approaches, making harmonization and resource synthesis very difficult. There are other land cover products that have been generated by prominent researchers such as Peter Potapov and Matthew Hansen, and they exist within the Global Land Analysis and Discovery database. But the problem with these data sets are that they are limited to a single land cover class or to a very short time period. Now, with a 1.2 degrees centigrade rise in global average temperatures and an anticipated 2 to 5 degrees centigrade rise expected by the end of the 21st century, there has been evidence that climate change is negatively impacting our environment, with worst-case scenarios expected for the future. Impacts have already been demonstrated on forest cover and land use patterns in several regions across the globe. For example, in the continental United States, a study by Mu et al. In 2017 showed that climate change would cause substantial reductions in croplands and marginal lands and pastoral lands in this region by the year 2070. In another study conducted by Lopez et al. Within the Amazon forest of South America, they showed that climate change would cause over 30 to 35% loss in forest cover in this region by the year 2050. In European landscapes, studies by Carozzi et al. In 2022 have shown that climate change will cause between 6 to 7% loss in croplands and grasslands in this region by the end of the 21st century. But despite this evidence, limited information is available in the scientific literature on the contributions of climate change to forest cover and land use change in the Congo Basin and on how this will look like in the future. Now, addressing these key issues usually require the use of powerful computational tools such as machine learning models, and these models are often designed with linear or nonlinear statistical or probabilistic modeling approaches to train, recognize, and predict patterns in a given data set using either a supervised or unsupervised modeling approach. Several machine learning models have been developed and tested for land cover mapping within several geographic regions across the globe. Prominent examples include like artificial neural networks, which use a set of interconnected nodes to accurately classify satellite images using a backpropagation approach and following a supervised training of sample data set. Another example is like random forests, which are an ensemble of machine learning models that use bootstrap techniques to build many single decision tree models that are being averaged or voted at the end to produce land use and land cover maps. We have another example like support vector machines that are built with a radial-based function to identify optimal decision boundaries that separate two or more land use and land cover classes within a given satellite data. We have another example like the k-nearest neighbors, which are non-parametric models that perform land use and land cover classification based on the distance between k-closest samples drawn from a given training data set. So in a study by Katami et al. In 2016, they showed that these four algorithms are really very accurate in carrying out land use and land cover classification across various geographical scales and potentially outperform many other well-known classification algorithms, such as the maximum likelihood classification, decision trees, classification and regression trees, and many more. Now, in recent years, many studies have been attempting to compare the classification performance of these machine learning algorithms for accurate land use and land cover mapping, thereby reducing classification uncertainties that usually arise, especially with the use of coarse resolution satellite images. For example, we have a study by Davija et al. In 2021 that has compared the classification performance of support vector machines and random forests in accurately mapping foreign land cover data sets for Poland and Romania. We have another study like that of Bashe et al. In 2022 that have compared the classification performance of 4 machine learning algorithms for mapping land use and land cover within Charlottetown in Canada. There are several other studies that have applied similar comparison approaches. But despite this evidence, limited information is available in the scientific literature on the comparison in classification performance of these machine learning algorithms for effective land use and land cover mapping within the Afrotropics, especially in the Congo Basin, where satellite images are highly affected by clouds and are the only freely available option. Now, together with image coarseness, a lack of availability of cloud-free images increases land use and land cover classification uncertainties. And to deal with this problem, there is a need to compare the classification performance of several machine learning algorithms on smaller and cloud-free or less cloudy geographic areas, and then use the most performant algorithm for large-scale land use and land cover mapping. So such methodological approach could foster the advancement of knowledge in the application of machine learning algorithms for land use and land cover monitoring within tropical rainforest regions across Africa, especially with the use of coarse satellite resolution images, the only freely available option. Now, forest cover change, land use change, and climate change and forest fragmentation constitute major threats to wildlife biodiversity. Great apes in particular are already facing considerable declines within the African tropics, especially in the Congo Basin, where the density of human activities is increasing. In the Zanga-Zanga protected areas of the Central African Republic, for example, consultations conducted by the IUCN and UNESCO suggest that chimpanzees, gorillas, and elephants are losing the suitable habitats required for their survival, and their conservation requires rapid management intervention. So these key issues are generally addressed in this dissertation under 3 manuscript-based chapters. In chapter 2, titled Application of Machine Learning Approaches for Land Cover Monitoring in Northern Cameroon, published in Ecological Informatics, volume 74, I actually applied statistical and machine learning approaches using 4 classification algorithms to effectively map and quantify land use and land cover change in the tropical rainforest region in Central Africa called the Mayo Rain Department of Northern Cameroon, thereby providing a first attempt in comparing these algorithms within such a setting. In chapter 3, titled Monitoring Forest Cover and Land Use Change in the Congo Basin under IPCC Climate Change Scenarios, I used the most performant algorithm reported in chapter 2 to carry out a large-scale land cover mapping and projection for the entire Congo Basin under IPCC Climate Change Scenarios. And my specific objectives here were to generate accurate land cover maps for the Congo Basin for the period 1990 to 2020 and quantitatively assess decadal changes in land cover patterns, and then use this baseline information to project land cover to the year 2050 under various socioeconomic impacts and climate change. In chapter 4, titled Recent Decline in Suitable Large Mammal Habitats Within the Zanga-Zanga Protected Areas of the Central African Republic, published in Global Ecology and Conservation, volume 42, I actually produced spatially explicit species distribution models to map the spatial variability and changes in ape and elephant habitat suitability within the Zanga-Zanga protected areas for 2 survey years, during 2015 and 2020, using spatial data sets of eco-guard patrol activities, habitat fragmentation, land cover, human pressure, topography, and climate variability as model predictors. I identified priority habitats as well as key factors affecting species distribution. I quantified priority habitat loss and gain, evaluated the contributions of key factors to these changes, evaluated the relationship between suitable habitats among species, and finally identified overlapping priority habitats to aid conservation. So what are the main methodology results and conclusions from each of these manuscript-based chapters? In chapter 2, I actually started by acquiring Landsat images, Landsat 7 enhanced thematic mapper plus and 8 operational land imager images of northern Cameroon from the USGS Earth Explorer webpage for acquisition dates 17 November 2000 and 29 November 2020. With that, I loaded my images in R and carried out image pre-processing using various R packages, including the raster, RGDAL, RS Toolbox, and SP packages. And my reason for carrying out image pre-processing was to convert digital satellite numbers to radiance measures, thereby correcting internal sensor errors and then reducing atmospheric noise. And in the pre-processing process, I used 4 radiometric correction approaches, including the apparent reflectance model, which actually converted the digital Landsat band numbers to top of atmospheric surface reflectance. And then I applied the simple dark object subtraction and dark object subtraction approach, which carried out phase reduction and corrected for atmospheric scattering. And then I finally applied the cosine estimation of atmospheric transmittance model, which corrected for multiplicative effects of atmospheric scattering and absorption, and then produced images with correct band reflectance values. Now, the next is that with these corrected images, I carried out a stratified random sampling of training data sets using a balanced sampling approach. That is, I sampled each land cover class independently and then applied over 500 pixel sampling points for each land cover class similarly. So in doing my sampling, I used a protocol designed for mapping the global MODIS land cover data sets, as well as for mapping other existing data sets that have been produced by prominent researchers such as Matthew Hansen and Peter Potapov. With that, I carried out supervised classification with the 4 machine learning algorithms. And before doing that, I had to divide my training data set sampled into 80% test and 20% validation using the R-Caret package, and then predicting this test data sets against my set of covariates, which were my Landsat bands using the R-predict function. So here are the various models again, and their respective packages that were used. For example, the KNN model, which considered the KKNN package, the SVM model that used the radial base function package, the MLPANN, which used the NetNet package, and the random forest model, which used the random forest package. And for each of these modeling algorithms, I employed a set of tuning parameters as well as iterations, and then validated my modeling results using a confusion matrix, as well as by correlating them with other existing land cover products. So the main results that I generated are: first, I produced land cover maps for this region for the 2 years of study and for each machine learning algorithm, and then validated my classification accuracies. And my results showed overall accuracy, for example, for the ANN model of 84% to 96% between the both years of study. For the KNN model, the classification accuracy was between 90 to 91% for both years of study. For the random forest, it was between 90 to 99%, and for the SVM model, it was 89% for both years of study. With that, I could conclude that all 4 machine learning algorithms perform relatively well in mapping land cover within this tropical rainforest setting. But however, the random forest had the best overall performance, as it had an overall accuracy of between 90 to 99% for the both years of study, and potentially outperformed the KNN, SVM, and ANN models, which had overall accuracies of between 80 to 90% for both years of study. With that, I further validated my results by correlating them with existing land cover products, such as those generated for the MODIS global land cover data, as well as by other prominent researchers such as Peter Potapov and Matthew Hansen. And my results actually showed strong correlations between my maps and those existing maps. So with that, I quantified the area of land use and land cover class for each year of study, and also quantified the change between the 2 years, and then generated land use and land cover change detection maps, where I actually mapped the land use transitions. For example, transiting from one land cover class in the year 2000 to another in the year 2020. And with these results, I then came out with the following conclusions and future directions. So the first one is that I provide a methodological approach that could foster the advancement of knowledge in the application of machine learning algorithms for land use and land cover monitoring within the tropical rainforest regions across Africa, especially with the use of coarse resolution satellite images. The second one is that I showed that the 4 machine learning algorithms that were used in this study produced relatively good accuracy and could potentially improve classification uncertainties within tropical forest regions globally, consistent with evidence reported in other well-known studies. I also found that the random forest model performed the best for both years of study compared to the other 3 models and could potentially be the most suitable approach for mapping land use and land cover change within tropical regions across Africa, especially at larger geographical scales. So I therefore recommend that these mapping approaches be further tested within other forested areas across the African tropics, especially for those that remain underrepresented in the remote sensing literature. In chapter 3, I also started again by acquiring Landsat images for the years 1990, 2000, 2010, and 2020 for the entire Congo Basin using the Google Earth Engine platform. And with that, I carried out image pre-processing again by removing atmospheric noise, especially by taking off clouds from the images using the quality assessment bands of my Landsat images. And because cloud removal generally causes loss in image pixels, I used the approach of Midekisa et al. In 2017 in acquiring Landsat data for a 3-year window and then calculating the median satellite pixels for this 3-year window in order to fill areas of missing pixels for my images. I then again applied the approach of Midekisa et al. In normalizing my images using the normalized differential vegetation index and normalized differential water index, and then calibrated those images with nighttime light images from the National Oceanic and Administrative and Atmospheric Administration. Again, I carried out supervised classification using the same protocol developed for mapping global Moody's land cover datasets, as well as other datasets generated by prominent researchers such as Matthew Hansen and Tapotapov. And in doing this, I carried out stratified random sampling again, but this time using an unbalanced sampling approach because of the study area size. So with that, I again divided my data sets into 80% test and 20% validation. And then this time around used the random forest model, which was identified in chapter 2 as the best performance model to carry out supervised classification. I further went ahead to validate my results again with the confusion metrics, as well as by correlating them with other existing land cover products. Now, the next stage is that I carried out land cover projections for the year 2050, and by doing so, I acquired a set of predictor variables to carry out these projections. And examples were like climate-related variables, which I acquired from the IPCC AR6 Ensemble Climate Projections of the CM IP6 project. And then I went ahead to acquire forest fires and landscape topography. For example, forest fires were acquired from the Moody's Global Fire Products, and landscape topography from the USGS Digital Terrain Models. And then I further acquired socioeconomic data sets from published data sets by Chokavina et al. In 2018 and Potapov et al. In 2020. And then acquired population density data from the Vico Limestone climate and population projection data that were modeled under 3 shared socioeconomic pathways using the CM IP6 framework of the IPCC. The next stage is that I created a set of land use and land cover transitions, and then identified the predictor variables that will easily influence these transitions, and then measured the percentage accuracy for each transition to occur under this set of environmental or human disturbance variables using the approach of Gibson et al. In 2018. So with that, I used those land use and land cover trajectories that I mentioned previously, where I created with my baseline data, which were 2010 and 2020, alongside a set of predictor variables in the AGC dataset land change modeler. With these trajectories, I applied them within the multi-perceptron artificial neural network framework of AGC dataset, which created land use and land cover transition sub-models that were modeled with the Markov chain algorithm of AGC dataset under 500 iterations and then aggregated at the end to project land use and land cover to the future. So what are the main results that I came out with? The first one is that I generated land cover maps for the 4 years of study and then validated classification accuracy for this 4 years of study, that's land cover maps for the last 30 years. And my overall accuracy showed 95% for the year 1990, 94% for the year 2000, and 95% for both the years 2010 and 2020. Again, I cross-validated my results by correlating them with other existing land cover products, again, like which are those generated by Peter Potapov and for the global Modis land cover dataset. And my results showed relatively strong correlations between these my datasets and those already generated at global scales. So the next is that I projected my land cover maps to the year 2050, but before doing that, I had to predict land cover datasets for the year 2010 and 2020 using the AGC dataset land change modeler and using the 1990 and 2000 baseline data in order to compare what the AGC dataset will generate for 2010 and 2020 with what I originally mapped with the random forest model using Google Earth Engine. And with that, my results showed relatively strong correlations between the data sets that were mapped with the AGC dataset, that were predicted with the AGC dataset for the year 2010 and 2020, and with that was already originally mapped with the random forest model for the years 2010 and 2020, suggesting that the AGC dataset land change modeler was really accurate in projecting land cover from a previous time step to a future time step. So with that, I had to now project my land cover maps to the year 2050 with the AGC dataset modeler and produced land cover maps under all 3 climate change scenarios. So with this, I quantified the areas as well as change areas between the different time steps, under decadal time steps, as well as under projected future time steps, and then assessed the change areas for classes that will be used for appropriate landscape planning. For example, with forest cover data sets, I actually showed that forests have declined in this region considerably over the last 30 years, with over 352,000 kilometers squared of forest loss over the last 30 years, and an anticipated 178 to 204,000 loss projected for the year 2050 under all 3 climate change scenarios. With croplands, for example, I showed that they have expanded considerably over the last 30 years, with over 84,000 kilometers squared of croplands expanded, and an anticipated 91 to 101,000 kilometers squared expansion expected for the year 2050 under all 3 IPCC climate change scenarios. Similar conditions were observed for built-up areas that have experienced expansions of over 45,000 kilometers squared over the last 30 years, with an anticipated 46 to 56,000 kilometers squared projected for the year 2050 under all 3 climate change scenarios. So with that, I actually quantified the key drivers of these changes, and my results show that key drivers of dense forest loss in this region included forest logging and forest clearing, maximum temperatures, wildland fires, population density, and distance to built-up areas. The main key drivers of built-up expansion were human population density and distance to built-up areas, while key drivers of croplands expansion were human population density. So with that, I drew the following conclusions and management recommendations. So the first one is that I provide a novel, reliable, and consistent spatial information on land use and land cover change in the Congo Basin that deals with the problem of data uncertainty and inconsistencies compiled by the FAO, as reported in Grenier 2008 and Matthews 2003. I also show that dense forests are declining at rates of over 0.3%, that is 11,700 kilometers squared per year, with over 8.6% or 352,000 kilometers squared of forests lost over the last 30 years. corresponding to findings that have been reported by Tiokavina et al. In 2018 and Kirilenko and Sejo in 2007. So with the loss in forest cover, I showed that there has been a continuous expansion in croplands and bird-up areas. And under human population growth and climate change, I project future trends which depict over 178 to 204,000 kilometers squared loss in dense forest, and between 46 to 56,000 and 91 to 101,000 kilometers squared expansion of croplands and bird-up areas, respectively, by the year 2050. So my results therefore fill a critical gap in knowledge about the current and predicted future states of forest and land use in this region and on the potential impacts of human activities and climate change. I recommend including these results within the United Nations Framework Convention on Climate Change REDD+ program in order to design a long-term regional strategy and action plan for monitoring long-term deforestation within the Congo Basin. In chapter 4, titled Recent Decline in Suitable Large Mammal Habitats Within the Zanga-Zanga Protected Areas, I started by acquiring occurrence data sets for great apes, that is chimpanzees, gorillas, as well as forest elephants, for the years 2015 and 2020, surveyed by a team of WWF biomonitoring assistant to the approach of distance sampling with line transects. So for this data set, I created species distribution models, but before doing that, I designed 7 experiments for these SDMs, which included 2 for chimpanzees, 2 for gorillas, 1 for elephants, 1 for great apes, and 1 for all 3 large mammals. So in carrying out my SDM modeling, I had to use a set of predictor variables, and I started by acquiring land cover data sets from the Copernicus Global Land Cover Products, and then acquired climatic data sets from the monthly Terra Climate data sets embedded in the Google Earth Climate Engine, which is a tool for visualizing and processing weather and climate data obtained from a compilation of different climatic simulations. I further went ahead to obtain anti-poaching patrol and human pressure data from the WWF Spatial Monitoring and Reporting tool, and then further acquired landscape fragmentation data sets by quantifying or calculating this fragmentation indices using the approach of Vogt et al. Using the ArcGIS landscape fragmentation tool. I then acquired topography data from the USDS digital elevation models. Now, before carrying out my simulations, the first thing is that I had to reduce reduce redundant variables through a Pearson's correlation test, and then applied a principal component analysis to exclude certain variables from highly correlated variables. And then with that, I ended up with 9 spatially independent predictors, which I applied in an ensemble species distribution models in R using generalized linear models and generalized additive models with migrate apes and elephant survey data sets for the 7 experiments as response variables, and then validated my models using the receiver operator characteristics and area under the curve values. And then with that, I generated individual species distribution maps for both years of study for each of the 7 experiments. And then I identified the most important factors affecting species distribution, and then quantified areas of species habitat suitability for the 2 time steps in ArcGIS. And then further went ahead to identify and map priority species habitats and areas of suitable habitat loss and gain between the 2 time steps in ArcGIS, and then use this as response variables within ordinary least squared regression models, as well as with my most important factors affecting species distribution in order to quantify the effects of key predictor variables to species habitat suitability changes, that is habitat loss and gain. So with that, I produced the following results. The first results are individual species distribution, or let's say habitat suitability maps for each of the 3 species under the 2 study period. And then I validated my model accuracies, which showed relatively strong accuracy of AUC values greater than or equal to 70%. So with that, I quantified the area of each habitat suitability for both time steps and then quantified the change in these areas. And my results showed that for chimpanzees, the suitable habitats for the species declined by over 96 kilometers squared, that is 2% points between the two time steps. For gorillas, the rate of decline was, the suitable habitats for gorillas declined by approximately 13.7% points, while for elephants, they declined by over 15% points. I further went ahead to generate habitat suitability maps for combined species, that is for great apes combined, as well as for all three mammal species combined, and then quantified the area of habitat suitability and change for between the two time steps. And my results showed that the suitable habitats for great apes declined by 13.3% point, while for all three large mammals declined by 16% point between the two time periods. Now, the next is that I identified the most suitable predictors that could predict species distribution, and my results showed that there were eco-guard patrols and human pressures that had the highest percentage contribution in predicting species distribution in my models. Now, with that, I created priority habitat suitability maps for all three species between the two time steps, as well as quantified the suitability areas between each protected area, as well as the changes. And my results showed that priority habitats for chimpanzees mostly occurred between the DSPA national parks, as well as within some special reserves, such as the ZCC, Kambi, and Yobe reserves, as you can see on the maps. And priority habitats for chimpanzees mostly declined within the Doki, ZCC, and Kambi special reserves. With gorillas, priority habitats also occurred within the GSPA national parks, as well as within some special reserves, such as the ZCC, again, Kambi and Yobe Jumbo special reserves, and actually declined within the Doki National Park, the ZCC, Luto Bilolo, and Kambi special reserves. With elephants, priority habitats occurred within all the entire GSPA protected areas, but declined considerably within all these areas, except for the Pluto Bilolo Special Reserve. The next thing is that I had to map overlapping priority habitats between species within each of these protected areas, and my results show that species habitats mostly overlapped within the GSPA national parks. So finally, I then quantified areas of suitable habitat loss and gain between the two time steps, and my results show that for chimpanzees, that over 276, 547, and 413 kilometers squared of all chimpanzee, gorilla, and elephant priority habitats have been converted to non-priority habitats over the 2 years of study, with declining areas highly and significantly influenced by human pressures. I further showed that over 92 and 343 kilometers squared of all ape habitats have been gained over the 2-study period, with habitat stability and gain areas highly and significantly influenced by increased eco-guard patrols. Now, what are the main conclusions and management recommendations that I came out with? The first one is that I generate habitat suitability maps for chimpanzees, gorillas, and elephants within the Zanga-Zanga protected areas and map changes between 2 survey periods. The second one is that I identified and mapped priority habitats required for planning species conservation, as well as quantified and assessed the impacts of key predictors to these changes. The next is that I provide evidence that priority habitats for chimpanzees covered about 1,300 kilometers squared of the entire GSP in the year 2015, while priority gorilla and elephant habitats covered over 2,500 and 3,000 kilometers squared respectively, with all three priority habitats for all three species declining by 4, 4.5, and 9.8% points respectively between the 2 time steps. Now, I found that these declines were primarily due to increased human pressure, consistent with evidence that have been reported in other parts of the Congo Basin. I further showed that species habitats overlap significantly and were spatially distributed mostly within the GSPA national parks, where there have been high rates of eco-guard patrols and reduced human pressure. So I therefore recommend increasing eco-guard patrol efforts within these sectors, and further suggest that Managers review zoning as well as use regulations of each sector within the GSPA in consultation with the indigenous and local populations as well as the private sector that exploits part of this reserve for logging purposes in order to facilitate social and ecological sustainability and the conservation of these endangered species. So now, what are the main general conclusions and how are these contributing to the advancement of knowledge in this dissertation? So the first one is that my dissertation research provides a novel focused analysis that compares the classification performance of multiple machine learning classifiers in small and large scale land use and land cover mapping within Afrotropical forest settings, thereby providing basis for selecting the most appropriate modeling algorithm required for projecting future changes under IPCC climate change scenarios. The second one is that I produced spatially explicit species distribution models to map and identify areas of priority habitats required for planning the long-term conservation of great apes within the Zanga protected areas, which is a region defined by the IUCN and UNESCO as facing increasing threats from human activities, and where EcoGuard patrol activities that were established for limiting these threats have not been fully assessed. The Congo Basin is just one such area of the world where these threats are highly alarming, especially as issues with socioeconomic neocolonialism, poverty, poor governance, and the inadequate participation of indigenous local communities in sustainable forest management keep increasing. So I therefore produce spatial data and findings that fill a critical gap in knowledge about the current state of forests in this region and on potential impacts of human activities and climate change. And my results also contribute to our understanding of great apes conservation biology and provide tools and data to help secure their future within the Zanga protected areas. So I give special thanks to my supervisors, Dr. Sarah Tuna and Damon Matthews, for supporting me in this project for the last 24 years. I also give special credits to Dr. Paul Gorang and the entire WWF team in the Congo Basin. I also give credit to Dr. Victor Traksh from the Warsaw University of Life Science, as well as to Anna Maria, who supported me for my tax funding for my Congo Basin project, as well as with Jessica Park from WWF Canada that also supported with matching funds. I also give a special thank you to all my lab members, that is the PICE and Climate Lab, and to you all my thesis examiners for accepting to be part of this committee and part of this defense. And then I finally give special recognition to my family members and friends that have supported me in one way or the other. And then now the big part of the credit goes to all funders of my research. So thank you very much for listening to my defense.
Thank you, Lisa. Thank you. Also, thank you on excellent timing. That is exactly 40 minutes. That was amazing, spectacular. So I'll now open, if you're ready to proceed, I'll.
If I can just stop for the recording.
Yes.
Sorry to interrupt.
Yeah, oh, no problem. Yes. So if you